Welcome to Mickey Study Circle channel. In this video, we shall see how to do the stress analysis of the stepped bars which is subjected to the varying loads using the ANSYS APDL software. So before we move on to the problem statement, let us try to visualize what a stepped bar looks like. So as you can see in the figure here, the stepped bar is having a varying cross-sectional area and it is composed of two different elements, that is element 1 and element 2, each of them with different material properties and geometrical properties. So we can assume that the element 1 is having a cross-sectional area of A1 and element 2 is having a cross-sectional area of A2. Also, L1 represents the length of the element 1 while L2 represents the length of the element 2. So in order to convert this physical continuum into an FEA model, we can model it using three nodes, that is node 1, node 2 and node 3. So as you can see here, the node 1 is constrained and the node 2 represents the change of the geometry from element 1 to element 2, and node 3 is placed at the end of the element 2, and the force of magnitude F is acting over the node 3. So this is about the FEA model of the stepped bar. Now let us move on to the problem statement. So we have got a composite bar which is shown in the figure, and it is consisting of three different parts, that is AB, BC and CD, and it is also subjected to the compressive loads as shown in the figure. While the magnitude of the load is 60 kilonewton, that is P1, and 75 kilonewton, that is P2. So we need to determine the extension of the bar and also the reaction forces and the stress distribution in each component of the stepped bar by assuming the Poisson's ratio to be zero point 0.3. However, moving on to the geometrical properties, the length of the component 1, that is AB, is 800 mm and the cross-sectional area is 2400 mm square, while its Young's modulus is 83 GPa. Moving on to the portion BC, so the length is 600 mm, while its cross-sectional area is 1200 mm square, and the Young's modulus is 70 GPa. And the next portion and the last portion of the composite bar here is CD, which is having a length of 400 mm, while its cross-sectional area is 600 mm square, and the Young's modulus is 200 GPa. So here the problem statement details us completely about the geometrical properties as well as the boundary conditions, that is the constraints, and the load that is acting over the stepped bar, and also its material properties, that is the Young's modulus and the Poisson's ratio, which is common for all the three components of the stepped bar. However, since this is a 1D problem and the Poisson's ratio is not of much importance to us, so we'll just move on to the next step, that is the determination of the solutions through the strength of material approach. So now first let us calculate the reaction force in the component. So the first component of the composite bar is AB. So we do know that the reaction force is the force acting in the direction opposite of the applied force. So the portion BC is having a force of magnitude of reaction AB minus the 60 kilonewton, which is the actual force acting. So this is the equilibrium condition. So we can assume that the elongation of the portion AB, BC, and CD to be equal to 0 because both the ends of the bar is fixed. So the total elongation is equal to 0. So with this formula, we can write the equations for the elongation and determine the unknown values of the reaction force. So we do know that the forces of 60 and 75 kilonewton is already acting on the member. So substituting the values, we get the reaction at the portion AB to be equal to 60.60 kilonewtons, and the reaction at the component CD end is equal to 74 kilonewtons. So since there are compressive forces which is acting, obviously the reaction forces will be positive, that is 60.60 kilonewtons at the end AB, which is the extreme left end of the stepped bar, and at the extreme right end of the stepped bar we have got the reaction force of magnitude 74 kilonewtons. So let us see if we are getting the same values even in the ANSYS APDL. Moving on to the next component, that is the deformation or the elongation in the bar. So we have got the extension of individual portions given by the mathematical model delta L is equal to P into L by A into E. So where P is the magnitude of the load, L is the length of the element, and A is the cross-sectional area, and the E is the Young's modulus. So since it is a composite bar, each portion is having a different value of Young's modulus. So upon substitution, we get the extension in the portion AB, which is equal to 0.2433, and that of extension in the BC, which is equal to 1.5 into 10 to the power of minus 3 mm, while that in the portion CD is equal to minus of 0.248 mm. However, we do know that the addition of all this will be equal to 0 because the bar is constrained in both the ends. So the next component is the stress component in each element. So in the AB portion, the magnitude of the stress is given by the ratio of the force acting and its cross-sectional area. So upon substitution, we do get the value of the stress in the portion AB equal to minus of 25.260 megapascals, which indicates that it is a compressive stress. And next is the stress in the BC, which is equal to minus of 0.5196 MPa, that is megapascals, and the stress in the portion CD, which is equal to 123.96 megapascals. So with this, we have computed the reaction forces, the deformations, and also the stress in the component using the strength of material approach. So now let us take time to understand how the same model can be prepared using the ANSYS APDL and subject it into the boundary conditions and the load that is given to us in the problem statement, and determine the values of the reaction forces, stress, and also the deformation within the member. Start with the procedure using the ANSYS APDL software to compute the reaction forces, elemental stresses, and the deformation in the member given in the problem statement. So before we start, let us go for the preferences and select the domain structural and click OK. Go for the file and select change title and enter the title as the stress analysis of a stepped bar. Click OK and just right click and select replot, so you can just see that the title is appearing in the bottom left corner of the screen. So now let us go for the next step, that is preprocessor, wherein we are going to define the element from the ANSYS library. So select on element type and click on add, edit or delete and select add. And now let us call this element, that is 3D finite STN180 from the ANSYS APDL library. Click OK. So now you can just see that we have selected the element, that is link 180. Let us click close and go for defining the other properties. So first we shall start with the material properties. Click on material properties, select material models, select structural, linear, elastic, and isotropic. So now let us enter the Young's modulus values for all the three different materials. So first let us feed the value for the portion AB. So this is 83 E5, and the Poisson's ratio is zero point 0.3 as given in the problem statement. So click OK. So now let us go for material, select new model again, so that we are going to define the properties for the second portion of the stepped bar, because it is not a uniform material bar but it is a composite bar. So you can just see that by default it is telling the material ID is 2. So click OK and select isotropic again, and let us feed the Young's modulus of the second portion of the stepped bar, which is 70 GPa. So let us convert that into MPa, which is nothing but 70 E5, and the Poisson's ratio is zero point 0.3. Click OK. So you can just see that the material model number 2 is created. Now again go for material, select new model, and you can just see that a material ID with number 3 is created. Click OK, select isotropic and enter the Young's modulus as 200 E5. And next the Poisson's ratio is zero point 0.3. Click OK. So now we have defined the Young's modulus for the three different portions of the stepped bar along with the Poisson's ratio. So now let us just close this material model behavior window and let us go for defining the sectional areas. So go for sections, and we have selected the element as link. So click on link and click on add. So first let us name the portion as 1, for that is AB portion. Click OK. So for our reference, let us just give the name for the section as AB and enter the geometrical properties, that is the cross sectional area, which is 2400 square as given in the problem statement. So to repeat the step, click apply and change the section ID to 2 and click OK and enter the section name as BC, followed by the sectional cross sectional area, which is 600 square as given in the problem statement, that is 1200 square. Click apply. Next, for the portion BC, it is 2. For the portion CD, it is 3. So click OK. So enter the name as CD and the cross sectional area, which is 600 square as given in the problem statement. So now we have concluded defining the geometrical properties. So click OK. So to repeat, click apply, and to end the process, click OK. So now this particular part, that is defining the area of cross section, is over. So now let us go create the model. So select modeling and create. So let us directly create the finite element model using the nodes. So go for nodes and select inactive CS. So that is inactive coordinate system. So the first node is always the origin. So type the node number as 1 and click apply. Next, the second node. So the second node is the endpoint of the portion AB, so which is having a total length of 800 from the origin. So enter 800, that is the x direction. So y and z coordinates are 0. So click apply. Next node is number 3, which is the end point of the portion BC. So it is 800 plus 600, which is 1400. So click apply. Next is the node number 4, which is the end point of the entire stepped bar. So 1400 plus 400, which is 1800. So click OK. So now you can just see that we have got the 4 nodes created in the active coordinate system, that is node number 1, node number 2, 3, and 4. So now we need to establish the connection between these nodes through the elements. So for that, select create and go for elements and select element attributes. So now we are going to define the portion AB, which is defined by the nodes 1 and 2. So the element is link 180 and the material number is 1. So this material number 1 is taken from the material props here. So you can just see that the material number 1 is going to have the values of 83 GPa and zero point 0.3, that is Young's modulus and the Poisson's ratio. And next the section is AB. So click OK. And now go for auto numbered, select through nodes and select node 1 and node 2. Click OK. So again, go for element attributes. We are going to define the portion BC. So the material is 2. The material number is 2, which is having the details of the Young's modulus and the Poisson's ratio as 70 GPa and zero point 0.3 respectively. And now let us define the cross-sectional area, which is given by 2 BC. So that is the cross-sectional area of 1200 square. So click OK. And now go for auto numbered through nodes. Select node number 2 and node number 3. Click OK. Again, go for element attributes. Let us define the last portion of the stepped bar. So material number is 3, having the Young's modulus of 200 GPa and Poisson's ratio of zero point 0.3. And the portion is 3 CD, which is having the geometrical properties, that is the cross-sectional area of 600 square. Click OK. Again, select in auto numbered through nodes and select node number 3 and 4 and click OK. So in this way, we have created the FE model of the stepped bar having totally 4 nodes. So this completes the assigning of the geometrical and the material properties, followed by the creation of the FE model. So now let us go for the next step in the FE analysis, that is the assigning of the boundary conditions and the loads. So now let us go for loads and select define loads. Select apply, structural, displacement, and since the geometry is created directly using the nodes, let us select on nodes. So as from the problem statement, we can see that the 2 endpoints are fixed. So select node number 1, click OK, and select all DOF, that is all degrees of freedom, which is comprising of both 3 rotational and 3 translational degrees of freedom, and the value is 0. The displacement value is 0. Click OK. So you can just see that node number 1 is now constrained with all the degrees of freedom. Similarly, again in the displacement, select all nodes and pick the node 4. Click OK. So select all DOF and enter the displacement value as 0. Click OK. So now you can just see that the node number 4 is also constrained from all the degrees of freedom. So now it is time for us to apply the forces. So the force is acting at node 2 and at node 3. So let us use the command prompt to enter the command for the force. So typing F initiates the software to understand that you're feeding the value of the force. So F is the library value for force. And at node 2, the force is acting. So the lab is the direction. So that is Fx is the direction, which means to tell that the load is acting in the x direction. And next is the value. So the value here is minus 60 kilonewton, that is 60,000 newtons. So minus indicates that it is acting towards the origin. So click enter. You can just see that the node number 2 is having a force applied here. Next is at node number 3. So go for F. The node number is 3, followed by the direction which is Fx, and the value is minus of 75,000 newtons. So this is the syntax for entering the forces. So at node 2 and 3 there are point loads acting, and at node 1 and 4 the displacements are 0, that is the degrees of freedom is constrained to be 0. So now we have completed the application of the boundary condition and the loads. So now it is time for us to solve the FE model along with the boundary conditions and loads. So select solution, go for solve, and select the current load step. So it is asking begin the solution of current load step. So permit it by telling OK. So you can just see that the solution is calculated. So click close and close this window also. So now it is time for us to extract the result. So let us go for general post processor and let us try to extract the first set of solutions, that is the reaction forces. So go for list results and select reaction solutions and select all items, click OK. So now you can just see that we are having at node 1 and 4, wherever the support is provided, the reaction forces are existing. So at node 1, the reaction force is 6624 newtons or 60.624 kilonewtons. And at node 4, that is at this point, the load is the reaction force is 74.376 kilonewtons or simply 74,376 newtons. So which is very close to the theoretical values obtained by using the strength of material approach. So this is the reaction solution. So now let us go for extracting the displacement value. So in the same table, that is list results, go for um, nodal solutions and select the degrees of freedom solution and select the x component of the displacement and click OK. So now you can just see that these are the displacement values. So we have already predefined that the displacement at node 1 and 4 is 0 because it is constrained from all the degrees of freedom. So there is no displacement. And at node 2 and 3, this is the value of the displacement, that is minus of 0.24347 and minus of 0.24792 E02. So this is the displacement values. So just click close after recording it. So now we can just go for plot controls and select style, size and shape and click on the display of element, click OK. And now we can go for creating the animation of the deformation. So go for animate under plot controls, select the deformed shape and deform plus and deform, click OK. So you can just see that the deformation is animated here. So this is the elongation in this direction of the application of the force, and also the maximum value of the displacement is shown up on the screen, which is equal to 0.002479 mm. So you can just click close. So the animation stops. So you can just go for view and select isometric. So this is the isometric representation of the 3D model of the bar that we have created. So this is the last portion of the stepped bar, the middle portion, and the starting portion of the stepped bar. So now it is time for us to extract the results for the stress in each element, which is element 1, element 2, and element 3. So now what we do is we enter SET as the command in the command prompt and click enter. And now let us go for selecting the element table and select define table. Click on add, and here let us select by sequence number and select ls. So ls represents the linear stress, so enter 1. So the 1 indicates the notation given in the ANSYS library for the link 180 element to extract the value of the stress for the model created. So click ok. So you can just see that I've chosen the label as ls1. Okay, so this is the stress element. So go for plot results, select contour plot, select element table, and here you can just see that we have defined ls1 from the previous step. Click s average, click ok. So this is the distribution of the stress within the member. So you can just see that the minimum stress is minus 25.2598 and the maximum stress value is 123.961 megapascals. So this is the value of the stress, and this is the legend which represents the distribution of the stress in the material. So now we can go for extracting the other results. So go for list results and select the element solution and go for stress and select the x component of the stress or the one minus stress. Click ok. So you can get the stress on each element. So this is the element 1, so this is the stress value, and this is the element 2, and this is the value of the stress, and element 3, this is the value of the stress, that is 123.96.51 and 25.26. So this is how we compute the values of the stress using the FEA software and record the results. So everything is done using the calculations that we learn in the theory FEM classes. So this is how we extract the results. So now in order to put up the results in multiple windows, so we can select plot controls, select multi-window layout, and select two, top and bottom. Click OK. So now again go for plot controls and select multi-plot controls. So select window 1, entity plots, click OK. And here I'll go for deformed shape, click OK. Deform plus and deformed, click OK. So right click and select replot. So you can just see that in the window 1 I'm getting the value of the deformation presented. So next go for plot controls again, select multi-plot controls, select window 2 and entity plots, click OK. Go for element solution, click OK. Select stress and then select the one minus stress, deform plus and deform, click OK. Select replot, so you get the distribution of the stress within the material. So in order to have this in the isometric view, just go for view and select isometric, and you can just zoom in and zoom out to fit the model into the screen or the window. So you can just see that the deformation and as well as the magnitudes of the minimum and the maximum stress, that is mn stands for minimum and mx stands for maximum stress, is being displayed here, and the color code represents the distribution of the stress values as per this legend. So you can just see that the maximum stress is in the last portion of the stepped bar, and the minimum portion, the minimum stress is in this particular portion of the stepped bar, so as per the legend that is represented here. So now in order to extract the uh, image of this particular analysis in a white background screen, what we can do is go for plot controls and select write meta file and select invert white or black. And now you can just see that it is going to be saved as an enhanced meta file. So let me just give the file name as 1D stepped bar and click save. So in order to extract the PNG file, so just go for the destination into which the particular file has been saved. So this is the file. So I'll just open this. So you can just see that it has been saved as a screenshot in the white background. So go for file and select as save, and you can just save this as a png file or a jpeg file. Click save. So now the emf file is converted into the uh, image file, so you can just see that. So this is how you extract the screenshot of the results. So with this we complete the computation of the reaction forces, the deformation and the stress values using the ANSYS APDL software for 1D stepped bar with three different materials. So it is a stepped composite bar. So with this we end the video after having recorded the required parameters. Thank you all for watching.